topic is entitled Vectors in R2. Vectors in R2. First thing I'll talk about is notation. Usually you denote vectors by lowercase u, v, w. That's usually. And to denote that it's a vector, we put a vector hat above it. In the textbook, the way they might denote it's a vector is by making a boldface. But of course, I'm not going to do that. I'll just put the vector hat on front of it. On top of it, excuse me. So, how do you draw a vector? Well, first, some more notation. How do you denote a vector? How do you denote an exact vector? Like, what is vector u equal to? You can easily say vector u is 3, 2, for example, or 3, 2. That is, you can write it horizontally. The first number is x and the second is y. Or you can write it vertically. X on top, y beneath it. If you wanted to draw, put the vector hat on top. If you wanted to draw the vector 2, 3, which of course could have been written this way, either or, all you do is you go very similar to plotting a point. You go to the point 2, 3. 2 on the x, 3 up on the y. You go to this point 2, 3. And then you draw a dot at the origin, and you go to 2, 3. And at 2, 3, you put an arrow. That is vector u. Vector u is 2, 3. The part that has the arrow, or the end that has the arrow, is called the head of the vector. The other end of the vector is called the tail. The vector does not, the tail of the vector does not always have to be at the origin. But if you're just told vector v is 7, -2, then it is. Then it is. You go to 7 on the x, you go to -2 on the y. That's the point 7, -2. Do not forget to label your axes, and you're almost done. We are now done. And we should label the vector. I just drew the vector v, which is 7, -2. What does it mean for two vectors to be equal? What does it mean for two vectors to be equal? Well, first, I want to comment that two vectors are the same vector, that is equal, if they are the same length, also known as the magnitude of the vector, and it's in the same direction. In other words, this vector u, it has some length, and it has an angle off the x-axis. If you imagine another x and y-axis right there, the horizontal dotted line is parallel to my x-axis, and the vertical one is parallel to the y-axis. If you have the same angle theta, and this length is the same as this length, let me make it a little bit longer, then that's also u. And the head is right there, and the tail is right there. These dotted lines are not really there. Those two vectors are the same. vector u, and so I already wrote u, let's call it u prime. U and u prime are equal to one another. You can move vectors, but the lengths of these two vectors, the original and the one that was transformed, when you move, those two vectors are equal if they are the same length and they make the same angle with the horizontal. You don't like the word horizontal? Not a big deal. You can talk about this angle phi, the one with the vertical. So if over here you have another axis, this vector v and v prime, they're both the same length and they both have the same angle off their y-axis. Those two vectors are equal, v and v prime. You can move vectors. You can't make them longer, you can't make them shorter, you can't change their direction, can't change the angle. You just move it. Move it straight up and to the right, or straight up and to the left, or down and to the left. Can't rotate it. Now, if vector u is equal to, say, u1, u2, and vector v is v1, v2, vector u is equal to vector v if and only if u1 equals v1 and u2 equals v2. u1 equals v1, that is, those two are equal, and these two are equal. Of course, I could have written u, the x and y components of u, horizontally. It doesn't matter. Your teacher or textbook may use one and not the other. Notice that this vector, the way it's written, it starts at the origin. The tail is at the origin. This vector, or v equals this vector, it starts at the origin. So, for example, 2, 5, vector 2, 5 equals vector 2, 5. Vector 3, negative 1 does equal vector 3, negative 1. 2, 7 does not equal to negative 2, 7. The x values are different. 3, negative 9, it does not equal to 3, 9. The y values are different. You want the x's and y's to be different? No problem. Those two vectors are not equal. The x's are different, the y's are different. Hence, not equal. Now, how do you write a vector in this x, y format if it doesn't start from the origin? What if it doesn't start from the origin? Again, if you were to write vector w is equal to 2, 1, well, in this notation, that means it starts at the origin and it goes over to 2, 1. Comes right here. That is vector w. Okay, that is vector w. Okay, wonderful. Well, what if a vector goes from this point P1 to that point up there, P2? Suppose you have that. Goes from 2, 1 to 5, 4. Now, if I can get this vector to start at the origin, don't change the angle, don't change the length, well then, wherever the head is at, that's what I'll call it. If this head was at AB, then I would say, let's call this vector V, then I would say vector V is AB. Vector V is AB. Okay. So what we're going to do to each and every point on this vector, remember this is 2, 1. I'm going to bring every point on the vector down 2 and 1 to the left. That brings the tail to the origin. I'll bring this point right here, I'll bring it down 2 and 1 to the left. It puts me there. I'll take this point, which is 5, 4. I'll go down 2 and 1 to the left. Here is my new vector. That is my new vector. Now, well, the question is, while I erase where I put the point 2, 1, this is now in the way, P1 is the point 2, 1. So the question is, what is that point right there? Now, like I said, I'm going down 2 and 1 to the left. I'm going down 2 and 1 to the left. Well, if I'm going down 2, that means I'm taking away 2 from the y. And if I'm going to the left 1, that means I'm taking away 1 from the y. That vector v is 4, 2. You do the head minus the tail. You do head minus the tail. So, one might denote this as P1, P2, and we're going from P1 to P2. That is, the head is at P2. If I put the head at P1, then this is not usually written, it's not usually written that way, but that's acceptable. But generally, instead of that, you would write you're going from P2 to P1. Usually the arrow always goes to the right. It starts at P1, it starts at P2, and goes to P1. So if you're given 2 points that make up the endpoints of their vector, and they're told which one's the head, you can get their tail to be at the origin, and then you can write it in the regular form. Let's try one more. Suppose you have a vector that goes, well, just so I don't have to write on it again. Suppose that P1 is negative 2, 3, and P2 is negative 4, 6. Negative 2, 3, and negative 4, 6. That's P2. Now, the vector goes from P1 to P2, because I'm putting the arrow at P2. So now, the question is, what is P1, P2? What is the vector that goes from P1 to P2? In just standard form, x comma y. You do head minus tail. 6 minus 3 on the y, and negative 4 minus the other x value, which is negative 2. And you get negative 2, 3. That is, coincidentally, it goes right to the tail. It didn't have to be there. And this blue and black line, these two lines, the blue and the black line, they really should form a straight line. And the reason I'm saying that is because the way I drew it, this angle and that angle are not the same. It'd only be the same if the blue and the black line formed together a straight line. But to over-exaggerate, it looks something like that. One of those, maybe the first line should have been drawn that way. You do the head minus the tail. Do one more of these. They're important to know. So, since you know how to subtract, you shouldn't do a million of these problems or 20 of them. Spend more time saying, if you're given 2 points and you want to write it in vector notation, x comma y notation, or this type of notation, you do for the x, you do the head x minus the tail x, comma, the y head minus the y tail. It's always the head minus the tail. So for example, if you have that vector, and I am telling you, P1 is negative 3, 5, and the point P2 is negative 1, 2. Well, we're starting at P1 and we're going to P2, because the arrow goes to P2. Notice, the arrow is still going to P2. The head minus the tail. It's the head minus the tail. It's negative 1 minus the negative 3, comma. The head y value is 2, and the tail is 5. This is the head, that's the tail. It's always head minus tail. And when you subtract those 2 numbers, you get 2. And when you, subtract those 2 numbers, you get negative 3. If you wanted to draw this vector, and you should, here is a 2, here is negative 3. So I just drew it. And again, hopefully your teacher's not going to take out a ruler. But again, if you were to, say, connect those 2 points with a straight line, both of those vectors should be on that line. Both of the vectors should be on that line. The initial vector which was given, and the vector you obtain when you move it to the origin. All I did was move this point down 5 and 3 to the right. I went down 5 and 3 to the right. So I take the tail, I go down 5 and 3 to the right, means I add 3. And I'll get the answer that I got down here. If you prefer, since I did say you subtract, you take the head, negative 1, 2, and you minus the tail, which is negative 3, 5. And this number minus that number is 2, and that number minus that number is negative 3. However you like to do it. You need to find out where the head goes. The tail is going to go to the origin. The tail is going to go to the origin. The next thing that would be nice to know is the length of a vector. What is the length of a vector? In R2. Well, a vector has a line segment. It starts at one point, it goes to another point, and it has all the points in between. It's just the length of a line. you have this vector, vector u, and the tail is at, say, x, comma, y. Now look, I meant to say the head is at x, y, and the tail is at the origin. Well, why is that point right there, x, comma, y? Okay, and you really need to know that. The reason is because if you look straight down, you see x. That is, this distance is x. And if you look straight across, you see that number, y. This distance is y. But that's the same as this distance. The blue dotted line and this length, that line, they're parallel. Same length. So at the bottom right, we have a right angle. And this length is x, and this length is y. So Pythagoras would say this length squared, and the length of our vector is denoted by the vector with two lines on either side of it, the vector name. And that vector squared will equal to x squared plus y squared. So I want to know the length of the vector, not the length of the vector squared. So I take the square root. The length of vector u is x squared plus y squared, square root. That's the length of the vector if the vector is given in this form. And I'm not going to say this anymore, or that form. They're the same. If vector u is this, you square the x component, you square the y component, and you add them up. That gives us this. And then you take the square root of the vector. Now, what if the vector v starts at P1, which is, say, V1, V2, and I'm going to change that, X1, Y1. Suppose vector P is located at X1, Y1, and that's the tail. And the other end, the head, is x2, y2. Well, if I could get vector v to be at the origin, all I do is I square the x value of the head and the tail, and I add them up. And please, please, don't forget to take the square root of it. Well then, P1, P2 is nothing more than subtract the x values, x2 minus x1. Notice I did the head minus the tail, comma. I do the same with the y values. That is the change in x, comma, the change in y. And I'll put quotation marks around it because it might be negative. You know, let me not say that at all. How you compute the change in x and the change in y, you can do x1 minus x2 for the change in x. But nonetheless, so now this is in standard form. It's P1, P2 now starts at the origin, and the head is there. Well, once you have the head, you're done. The length of P1, P2 is equal to this, the x value squared, x2 minus x1 squared, plus y2 minus y1 squared, the square root. That's the length of P1, P2. Now that we're squaring it, doesn't matter if you get the change in x if you do it backwards. Whether you do x2 minus x1 or x1 minus x2, when you square them, they're equal. If here, this is negative 3, and down here is positive 3. Bottom line is, when you square it, doesn't matter. Doesn't matter when you square negative 3 or positive 3. You're going to get the same answer. You're going to get the same answer. So at this point, I can say that you just find a change in the x, you find a change in the y, you square them, add them up, take the square root of the result. I calculated the change in x, I squared it. Calculate the change in y, I square it. Add that up, and then put a square root sign above it. Okay. So, you don't have to do head minus. To find the length of a vector, you don't have to do the head minus the tail. You can do the tail minus the head. You'll get the wrong number. Instead of getting 5, you'll get negative 5. Or instead of getting negative 7, you'll get positive 7. But you're only going to square that number. So it doesn't matter what the sign is. It doesn't matter whether you square 9 or negative 9. You're going to get 81 anyways. Okay, so let us try another one of these. If u is the number 3, negative 4, the length of the vector u will be 3 squared plus negative 4 squared. And you should know that that's 5 squared. 3 squared is 9 plus negative 4 squared is 16. And you get the square root of 25, which is 5 squared. The square root of 25 is 5. And basically what you have is this. You have this is 3 and this is 4, or negative 4. Well, then that's going to be 5. I guess I should have drawn this instead. 3, negative 4, 5. Okay, but nonetheless, the length of u is 5 units. Now, think about it. What exactly does it mean, 3, negative 4? Well, maybe x is in inches. Maybe y is in inches. So if I'm going to actually say that, let me put negative 4 a little bit lower. Okay, so this is 5 inches. 3 inches here, 4 inches here. This is going to be 5 inches. If they're feet or centimeters, fine. Let them be feet or centimeters. Let them be miles. Doesn't matter. The units are what they are. Just make sure they're the same units. If they're different units, if x is in inches and y is in feet, well, you better convert both numbers, the x and the y numbers, to either feet, both feet, or both to inches, or miles if you prefer, or centimeters. They have to be converted to the same. Now, if you were told that point P is 5, 3, and you're told that point Q is 2, negative 2, and you're asked to find the length of PQ. That is, the vector starts at P and it goes to Q. So if I were to graph this 5, 3 is right here. And then 2, negative 2 is right here. So the vector goes like that. And we would love to know the length of the vector PQ. The length of the vector. Well, if you go from 2 to 5, you went up 3, x went up 3. And if you go from negative 2 to positive 3, you went up 5. And after all, if this is the ground floor, you're on an elevator, 0 is the ground floor, but you are 2 floors below 0, and you want to go 3 floors above. Well, first you go up 2 to get to 0, and then you go up 3 more to get to 3. 2 plus 3 is 5. 3 squared plus 5 squared, square root of 34. This vector is square root of 34 units. Now, what would it mean that two vectors are parallel to one another? What would it mean if two vectors are parallel to one another? For example, this vector and that vector are parallel to one another. Why is that? Because if I drew a horizontal line at the tail, those two angles are equal. Those two angles are equal. One is just longer than the other. There's no reason why they can't be the same lengths. I tried very hard for this last vector and this vector down here to be the same lengths. Draw a horizontal line. If that angle equals this angle, these three vectors are parallel. Now, what if I moved all the tails to the vertex, to the origin, I meant to say? What if I moved this tail and this tail and this tail right here? Well, one thing that's going to be true is that angle has to equal the other three. The only thing that might change is the size. Maybe the smaller vector, this one, only comes up to there. And the longer one, maybe it comes out further. What about this vector? This vector is parallel. This vector is parallel. Maybe I shouldn't have said you have to draw the horizontal line at the tail. You can draw the horizontal line. Let me do it here. You can draw the horizontal line here. Still, this angle and that angle are the same. That is, all of these 4 or 5 angles are the same. If I draw the horizontal line here, well, yeah, this angle and this angle and this angle and this angle and this angle, they're all the same. All right. So, if vectors are parallel, when you put them at the origin, one might go like this, the other one might just be longer, still starting at the origin and be longer. One might go in the opposite direction. Maybe you have a second one that goes in the opposite direction even more. What you can say is one vector is a multiple of the other vector. For example, if that point is 2, 3, and you double it, you get 4, 6. The vector that starts at the origin and go to 2, 3, and another vector that starts at the origin and goes to 4, 6, they're parallel. Because if you double both the x and the y values, you get the other point. One is a multiple of another. I guess we should talk about scalar multiples. C, a real number, times the vector x1, y1. Well, this is just C times the first component, comma, C times the second component. So here is a multiple of the vector x1, y1. 4, 6 is nothing more than 2 times that other vector, 2, 3. 2 times 2 is 4. 2 times 3 is 6. If one vector is a multiple of another vector, if this head is -6, -9, well, if you take 2, 3, this vector right here, if you take 2, 3, and you scale it by -3, you get -6, -9, which is the other vector. This vector and this vector are parallel because one is a multiple of the other. So let's formally write that up. Two vectors are parallel if one vector is a multiple of the other vector. Let me just erase my physical board and we'll be done. Two vectors, u and v, are parallel. That's the symbol for parallel. If one vector is a multiple of another vector. Like C times U is equal to V. Or U is a multiple of V. If V is C times U, then U is 1 over CV. If U is twice V, well then V must be half of U. These two statements are the same. U is twice V because U is half of V. The reason U is 2 times V is because V is the smaller vector. V is half of U. If this is V, I double it and I get U. The whole thing is U. But this part is V, or if you like, that one is V. So let's make it look like a V. Well, kind of obvious that two V's give you U, or remember, this whole length is U. Well, then half of that length is V. Is means equal. Need to be really smooth on converting English to math. Is means equal. U, if U is this part plus this part, and they're both V, so you can call this whole thing 2V, or you can call it U. That is, those two are equal. This whole thing is U. And that's exactly half. V is exactly half. Sorry, is exactly means equals. V is exactly half of means times U. V is half of U. Okay. So it doesn't matter whether you say U is a multiple of V or you say V is a multiple of U. They are can say one vector is a multiple of another vector, then these two vectors are 100% parallel. These two vectors are 100% parallel. So you might ask, are these vectors parallel? U is equal to 3, 5, and V is 4.5, comma 8. 4.5, comma 8. Well, you have to multiply 3 by something to get 4.5. And it better be the case that whatever you multiply 3 by to get 4.5, you have to do the same to 5 to get 8. Well, 3 times y gives you 4.5. The answer is 4.5 over 3. Now, even if you didn't know that that's 1.5, even if you didn't know that, well, take 5 and multiply it by 4.5 over 3, or take 5 and multiply it by 1.5. 5 times 4.5 is 22.5 over 3, and this 5 times 1 is 5, 5 times a half is 2.5, you get 7.5. And 3 into 22 goes 7 times, with 1 left over, and 3 into 15 goes 5. Okay. So if you multiply 5 by, so we found out what we multiply 3 by to get the other x value. You multiply 3 by 1.5, or if you insist, 4.5 over 3. But when I multiply 5 by that number, when I multiply 5 by 4.5 or 5 by 1.5, I'm not getting 8. This is not 8. This is not 8. Okay, so U and V are parallel? Not. U and V are not parallel. You have to be able to find out the multiple. You have to be able to find out the multiple. 3 times what gives you 4.5. Solve for that. Another way of doing it is to divide. If U is 8, 10, and V is 12, 15. Question is, are they parallel? Well, you can divide the x's. I chose the larger one. If I choose from the V, if I put the V coordinate on top, I have to do the same with the y coordinate of V. It goes on the top. And actually, we don't even have to reduce. Maybe this is the quickest way of doing it. The question is, are these two equal? Let me solve that over here. It's 12 over 8 equal to 15 over 10. Now you can cross multiply, but you're going to have to know what 10 times 12 is, which you should know, and you're going to have to know what 8 times 15 is. If you do, wonderful. This product is 120, and that product is 120. They are equal, so yes, the vectors are parallel. If you didn't know that, you can reduce. 4 goes into both of these numbers 3 and 2 times. And 5 goes into both of these numbers 3 and 2 times. Oh, yeah. They are equal. There's no question about it. They're equal. So maybe that's the way to do this. That's probably the cleanest way. Why don't we look at this last problem again? And I like bigger numbers on top. I'll put this x on top, and I'll put this x on the bottom. Now, it might turn out that things change. It might turn out that between the two y's, that one's smaller. But it doesn't matter. If I put the 4.5 on the top, I must put the 8 on the top, and the 5 on the bottom. The question is, are those equal? Now, if you have a command of math, if you have a command when you multiply 5 by 4.5, you're going to get a whole number 20, and then you're going to get 2.5. You're going to get 20 plus 2.5. And I'm keep going, but the key thing is you're going to get a half. 3 times 8 doesn't give you a fraction. It's 24. Okay, 22.5 does not equal to 24. So it's not equal. Hence, U and V are not parallel. U and V are not parallel. Just divide them and see. Because when you divide them, you're finding out what you multiply one x by to get the other x. And you're finding out what to multiply one y by to get the other y. And if it's the same values, then they're parallel. One vector really is a multiple of another vector. Okay, now on to some beautiful stuff. Suppose you have this triangle. You want to find the area of the triangle. And like every triangle, it has 3 vertices. The P1, we'll call that x1, y1. P2 is x2, y2. And P3 is x3, y3. And I will put the xy axes in place. Now, we want to find that area, but we're going to find that area this way. I'm going to do the following. If I bring this straight down, that x value here must be x1, and the y value is 0. If I bring this point straight down, the x value is x2, and the y value is 0. If I bring this point straight down, the x value is x3, and the y value is 0. Okay. Now, again, I want that area. Well, if I calculate this area, okay, and then I add on this area, I will have captured all the area in those 2 top triangles. The only problem is I have too much. I need to take away what's in here and in here. So let us calculate the area. I'm going to do it the way I just hinted. We're going to calculate the area of this rhombus. We are then going to add on the area of this rhombus, and then I'll take away the area of that rhombus. And what will be left is the area we wanted. Okay. What is the area of the left rhombus? Now, that left rhombus looks something like this. This point is x1, 0. This point is x2, 0. This point is x2, y2. And this point here is x1, y1. Now, if I were to rotate this 90 degrees, I would get something like that. And we're more used to that. Since this bottom line and this top line are parallel, that is, these two lines are parallel, we add up the two, we take the average of the two heights, we take the average of these two heights, h1 and h2, and since this is a right angle, base 1 and base 2, and then I multiply by the height. All the bases. If you go straight up, you start off at 0 and you end up at y1. You went up y1. Remember, the formula is add up the two bases, multiply that by the height, and then take half. So right now, I'm going, here's my half. I want the two heights. This height goes from 0 to y2. So I added up the two. Well, I'm calling these heights, but I'm using them as bases. Base 1. I'll call this base 1, that base 2. I added up the two bases, and now I'm going to multiply by the height. But this here is the height. That is, I'm using that as the height. x2 minus x1. You want to know how long this is, from 3 to 5. Don't you do 5 minus 3? I'm doing x2 minus x1. x2 minus x1. Erase this, and I'll put that down. And we have the area of the first trapezoid. Now, all the trapezoids are going to, the formula has a half. And that half, I'm going to factor all the way in front. I'll factor the half way in front by just putting parentheses after the half. And the height, like I said, was x2 minus x1. Plus, now we want to find the area of this rhombus. B1, B2, and I'll use that as the height. Well, this point goes from x3, 0 to x3, y3. It just went straight up. The x didn't change. This height is y3. Plus, remember, the half is in front of the formula, plus this height. Well, this point on the bottom was x2, 0, and then it went up to x2, y2. The x's didn't change. That makes this a right angle. That is, the y value just went from 0 to y2. That's y2. Times the base, x3 minus x2. x3 minus x2. Okay, so we have the area of that whole thing now. The two trapezoids, the left trapezoid and the right trapezoid. But like I said earlier on, that's too much. That's too much. I need to take away some stuff. And what I need to take away is the lower trapezoid. And once I take that away, we'll have the formula. I have to take away the lower trapezoid. The lower trapezoid, let me just make this bracket a little bit smaller. The lower trapezoid goes something like this. This lower point is x1, 0, x1, 0. The higher one is x1, y1. Over here, we have x3, 0. We have that vertex. And up here, we have x3, y3. Well, this one's more familiar with us. The bases, actually that's not true. So these two sides are parallel. Those are the bases. One of them is y1, plus the other one is 0 to y3 is y3, times the height, which happens to just be this, x3 minus x1. x3 minus x1. Now, what happens there is going to be amazing. Make this a little smaller. Okay. Close the bracket. Each of those terms inside those brackets should have a half in front. But I factored out half. Okay. Let us distribute this out and let's look at what we get. What we get with you. Well, we're going to do something after we get what we get. Now that's going to simply be amazing. We have y1, x2 minus y1, x1 plus y2, x2 minus y2, x1 plus y3, x3, y3, x3 minus y3, x2, and plus in front, plus y2, x3, y2, x3, minus y2, x2, minus y2, x2. And now we have to take away everything. We have to take away y1, x3. We have to take away negative y1, x2. That is, we add y1, x1. I have to take away y3, x3, y3, x3. And we have to take away negative y3, x1. That is, we add y3, x1. Let's see what cancels out. We have 4, 8, 12 terms. y1, x2. Do I see it anywhere else? And no. y1, x1, I see down here. First I weigh y1, x1, then I add it back. That cancels out. That cancels out. Now, I'm adding y2, x2, and then over here, the right, I'm taking away y2, x2. And I'm adding y3, x3, but then I take away y3, x3. 1, 2, 3, 4, 5, 6. Okay. So half the terms actually cancel out. Now, let me write down what we have. Remember, the 3 points were x1, y1, x2, y2, and the third point was x3, y3. We'll write down what that equals, and then we'll look at it a different way. We'll look at a determinant and see if there's a determinant that coincidentally gives the same answer. So we now know that the area of the triangle is equal to 1/2 times the remaining terms, y1x2 minus y2x1 minus y3x2 plus y2x3 minus y1x3, and then I think it's plus y3x1. Okay. Now, you can use that formula. You can use that formula. Maybe x1, y1 is a 0.34, and x2, y2 is 2, -5, and x3, y3 is 1/4. Okay, so you use that formula, and you would get the area of the triangle. You will get the area of the triangle. But here's something that is absolutely amazing. This is absolutely amazing this happens. If I write down the determinant, I write down the first point, x1, y1. I write down the second point. I write down the third point. And then I put ones. The determinant is going to equal to the one on top. Well, it's equal to what's in the brackets. That is, if half of that determinant, I should get what's on top. Or should you? Is it 100% reasonable that you're going to get what's on top? Is it 100% reasonable? And the answer is no way. I can easily see that we don't have to get the same answer. In other words, you were just given 3 points, and your classmate chose to write down that point first, and that point second, and that point third. Okay? But you didn't have to do it in that order. You didn't have to do it in that order. Your classmate wrote down x1, y1 first. I mean, you're just given 3 points. 3, 2, 5, 4 is the second point, and 0, 3, the third point. You're just given these 3 points. Okay? Now, there's no reason why this has to be the first point, and that has to be the second, and this one the third. One of your classmates could put this down first, and this down second, and this down third. First, second, third. But you, on the other hand, you want to write down this point first. x3, y3, and then write down this point next. That's the 2 point, x2, y2, and then write down this point last. x1, y1. And you put the ones down, and you say, oh, that's the determinant. Forget the half for a moment. These are not equal. These are not equal. Because to get the second determinant, I interchange 2 rows. I interchange 2 rows. Assuming this determinant is not 0, I interchange 2 rows. So they're not going to give me the same answer. They're not going to give me the same answer. When you interchange 2 rows, the sign changes. Okay? When you interchange 2 rows, the sign changes. So sometimes, if you did the problem, you'll get 11. And your classmate just switched 2 rows, and your classmate, she gets -11. Well, if one of you had to be right, it's you who got 11 and not your classmate who got negative 11. How can the area of a triangle ever be negative? Well, it is their matrix that I said. You write down the first 1 point, you write down a second point, you write down a third point, you put ones, and you take the determinant. But you have to take the absolute value of that determinant. And the formula is 1/2 the absolute value of that determinant. Now, let's see if this is really true. Let us first concentrate on this determinant. And I use cofactor expansions here. If I did row 3 minus row 1, 1 minus 1 will put a 0 there. If I did row 2 minus row 1, 2 minus 1, row 2 minus 1, 1 minus 1 would put a 0 there. So the determinants are still going to be equal. It's 1/2 the absolute value of the determinant. Row 1 did not change. Let me use a little bit more space. Row 1 did not change, but row 2 and 3 did. Row 2 minus row 1 is x2 minus x1. It's y2 minus y1 and 0. And I do row 3 minus row 1. Rows are x3 minus x1, y3 minus y1 and 0. Okay, this is equal to 1/2 the absolute value of that determinant. But this determinant is pretty simple to calculate because column 3 has only one non-zero entry. I will expand about column 3. So I only have to cross off column 1. Crossing off column 2 just crosses off a 0. Okay, so I get -1. The number that was crossed off twice is in the third column, first row. I meant to write 1 plus 3, but addition does commute. That number that got crossed off is a 1, and the remaining determinant is just this. x2 minus x1, x3 minus x1, y2 minus y1, y3 minus y1. This is 1/2 times the absolute value of what's in the big brackets. 3 plus 1 is even, so -1 to the 4 is 1, times another 1 is 1. 1 times this determinant is just this determinant. But this is a 2 by 2. You multiply these two out. You multiply these two, I meant to say. Minus, you multiply those two. Get x3 minus x1 times y2 minus y1. To be honest, I'm tired of this problem at this point. Here is just an elementary high school level problem you're left with. Multiply this out, multiply that out, subtract. And either you will get this or you would get negative this. Actually FOIL this out, FOIL it out, FOIL it out, subtract. You will get what's on top in the red or negative that. And the absolute value doesn't care about the negative. Okay. So everything that's going to remain on the board in a moment is the formula to find the area of a triangle, given the vertices. If you have the vertices, the 3 vertices that make up the triangle, it's a piece of cake. I love this formula. This is the greatest formula ever. If you want the area of a triangle, it's not hard at all. In the past, usually you called one side the base, and then you had to find the height or the altitude, and that involved cosines and sines and really needing a calculator. How do you find the cosine of 27 degrees without a calculator? But no more. This eats through it. You have this triangle. This is a 3, 1. This is 0, 3. And this will be 2, 3. Okay. Now, if you want, you can call this the base, drop a perpendicular line, and then find the height, and call it height. And then the area will be, first you'd have to calculate this length and that length. The area would be 1/2 times this length, the base, times the height. But that's way too complicated. The area is 1/2 the absolute value of this determinant. You're given the point 2, 3, and the point 0, 3, and a third point 3, 1, 3, 1, and you put 1s here. Calculate this determinant. You can use the spaghetti method. But since I always have 1s in that right column, I'll always do the same. I'll do R2 minus R1 and row 3 minus row 1. So I get 1/2 the absolute value of 2, 3, 1. 0 minus 2, 3 minus 3, 1 minus 3. No, I won't even bother doing the third one. I'm going to keep it the same. Why? Because coincidentally, that row has all zeros except one entry. So let's find out that determinant. It's -1. I'm expanding around row 2, but when it comes to crossing out columns, I only need to cross off column 1, because that's the only column when I cross off. I don't cross off a non-zero number twice. Like if I went down here, I crossed off 0 twice. If I went here, 0 twice. I always have to multiply by the number I cross off twice. Well, if I'm multiplying by 0, like I am in column 2 and 3, it's a waste of time. This -2 is in row 2, column 1. It is a -2. The remaining determinant is 3, 1 and 1, 1. You get 1/2 the absolute value of, this is an odd number, so -1 to 3 is -1, times the -2 is 2, times the determinant, 3 minus 1. Oops. 3 minus 1. I had 2 in my mind. 3 minus 1 is 2. So what's inside here is 4. 2 times 2. So you get half of the absolute value of 4. The absolute value of 4 is 4. Get half for 4, or 2. I found the area of that triangle without using a calculator. Just a simple 3 by 3 determinant. Normally I would do another one, but in a way I will. But it won't be a triangle this time. It'll be a parallelogram. Parallelogram is a four-sided figure where opposite sides are parallel and opposite sides are equal in length. It's a rectangle slanted on its side. Just like a rhombus is a lopsided square. Okay. There it is. Now, every parallelogram has something interesting. If you cut it, if you draw a diagonal, say that diagonal, you cut it into two equal triangles. So you have P1, P2, P3, and P4. If you wanted to find the area of triangle 1, you would use the three vertices, P1, P2, P3. You'd leave one out. And if you doubled it, you find the area of the whole parallelogram, P1, P2, P3, P4. If you instead wanted to find the area of the lower triangle, P1, P2, P4, well, you would calculate the area of that triangle using P1, P3, P4. Notice, let me just write this down. First times through, we didn't use P4. Now, we're not going to use P2. And if we find out this area down here, we'll double it, and we'll have the area of the whole parallelogram. Okay? But I didn't have to draw that diagonal. There is another diagonal. What if I drew this diagonal instead? It, too, cut this parallelogram into two equal triangles. Two congruent triangles. Triangles 3 and 4. Now, if I wanted to find the area of triangles 3, well, triangle 3 uses vertices P4, P1, and P2. That is, it doesn't use vertex P3. Okay? And you find the area of the upper triangle, upper left triangle, and then double it, and you'll have the whole area. Because if the upper area is 7, so is the lower area 7. Just double 7, and you get 14. If you wanted to calculate the area of triangle 4, you would use P4, P3, and P2. That is, you wouldn't use P1. All you do is pick any 3. That is, leave one out. Just leave one out. If you want to find the area of a parallelogram, the formula is the absolute value of that determinant. It's no longer half the absolute value of that special determinant. It's no longer half the value, because the area of a parallelogram is twice the area of that triangle. Every parallelogram is made from two triangles. If you have this triangle, you could go parallel to this line, and then parallel to the bottom one, and there's your parallelogram. There is your parallelogram. Okay, so I'm going to give you a parallelogram, and we're going to compute the area of the parallelogram. And it's a very simple process to do. Again, it's just one determinant. Find the value of one determinant and take the absolute value of it. So suppose you have this are parallelogram. I want you to think it's a rhombus. Okay. So this is 3, 5, and this is 7, 5, and this is 4, 6. So this is going to be 8, 6. So the question is, what's the area? Well, you know, whether you draw this or not, I just split it into two equal triangles. Let us find the area of triangle 1. That is just, so it's going to be A is equal to the absolute value of this determinant. Just write down 3 points. 4, 6, 3, 5, 7, 5. Leave one out. Just leave one out. And 1, 1, 1. Okay. Now, coincidentally, row 2 and 3 are almost the same. They just differ in the first coordinates. The 5s are the same, the 1s are the same. I'm just going to do row 3. I'm changing row 3, so I just wrote row 3. I didn't write negative row 3 or 2 row 3s. And then I'm taking away some multiple of row 2. 1 multiple of row 2. And I'm going to get the absolute value of the first row did not change. The second row did not change. The third row changed to this. Third row changed to this. And now I'm going to expand about row 3. And I only have to cross off column 1. So I get the absolute value of negative 1. The entry that got crossed off is in row 3, column 1. That entry is a 4. And the remaining determinant is 1, I think. 6, 1, 5, 1. 6 minus 5 is 1. Negative 3 plus 1 is even, so negative 1 to the 4 is 1, times 4 is 4. The absolute value of 4 times this is 1. 4 times 1 is 4, and the absolute value of 4 is 4. This parallelogram has an area of 4. And earlier I said we didn't have to do another triangle. And the only difference between the triangle and what we did here is triangle, you have a half in front. You would have half. You would take half of 4 and get 2. But we're not taking half because it's a parallelogram. That is just a minor difference between a parallelogram and a triangle. Any triangle you draw, you could complete it and make a parallelogram. Through this point, I'm going to go parallel to that line. I don't know how far I need to go, okay? Through this point, I go parallel to this line. Okay, erase the excess, and you just drew a parallelogram. This is pretty neat stuff. We can use determinants to find areas of parallelograms and triangles. So from now on, you don't have to find the area of a triangle. You don't need to know anything but determinants. And if you forget your determinant rules, you don't even have to reduce the determinant. You're always going to get a 3 by 3 determinant, and you just use the spaghetti method. Okay, the spaghetti method always works for 3 by 3s. Okay. Now, I'm going to talk about adding 2 vectors. I'm going to talk about adding 2 vectors. Suppose you have vector u and you have vector v. You want to add them. Well, remember, you can move vectors. Just can't change the size or the angle. That is the direction. To the best of my ability, I drew u again. Now, I'm going to put the tail of v at the head of u. And v goes in this direction. That's v. U and then v. And where I end up, which is namely right there, that's going to be where u plus v ends up. This blue vector is vector u plus vector v. That's u plus v. Vector u is x1, y1, and vector v is x2, y2. Well, then vector u plus vector v, first you add the x components, comma, and then you add the y components. Graphically, it's what I just said. Now, there's another way of doing this. What you can do is go to the header v and go parallel to u. Maybe more than you need to. And then you go to the header u and you go parallel to v. Like that. And you erase the excess. And you say, that wasn't so bad. And you're like, what are you talking about? Well, here's what I'm talking about. That blue vector is u plus v. Why is that? Because this vector right here is v. That vector right there is v. If you start here and you end there, and then you start here again and end up there, well, then that's the sum. The directions are very, very important. You have to put the tail of v by the head of u. Or you could have put the tail of u by the head of v and go that way. That is, you never even had to do this one. But the bottom line is you get u plus v. It's just completing the parallelogram. You're just completing the parallelogram. And the diagonal will be the sum. Sometimes, and we'll see this in a few minutes, sometimes the diagonal might be the difference. If u is 3, 1, and vector v is negative 2, 3, well, if you just add them, get 1, 4, and this will be u plus v. U plus v will end at 1, 4. Here is 3, 1. That is vector u. And vector v is negative 2, 3. Negative 2, 3. This is vector v. If you complete the parallelogram from v, from the header v, I go parallel to u, which is that way. And then from u, from the header view, I go parallel to v, which is not that way, but rather this way. I erase the excess. And remember, I don't have graph paper, etc. But this here is u plus v. And it actually doesn't look bad. 1, 2, 3. And let me just get rid of this right here, because it's smack in the way. If you use graph paper, you'll get exact answers. Well, if this is 1 and 2 and 3, well then that looks like 4. And yeah. That's 1, 4. Exactly what the sum was. So it is working. But if you want to add two vectors, again, it's much easier than I've been showing. If this is vector u, and this is vector v, and you want u plus v, that is, you're adding the left side of the equations, you have to add the right sides. 3 plus negative 2, 1 plus 3. And there is u plus v. It's 1, 4. Okay? And my graph agreed with it. Take it as a built-in check. Make sure that, you get 1, 4 adding the two vectors, but when you draw it, you get negative 3, negative 9. Like, whoa. 1, 4 and negative 3, negative 9 are nowhere near one another. Something went wrong. Okay. I've already defined what c times u is. If u is xy, you get cx, cy. Now, let's talk about the directions. If c is bigger than 0, then cu is in the same direction as u. If c is less than 0, then it changes. Cu is in the opposite direction as u. In other words, if this is vector u, if that's vector u, ends right at, ends there. Well, 2u, or half of u, would be that. That'd be half of u. 2u would be that. Negative u would be that. This length and this length should be the same. That would be negative u. If I go twice as far, that would be negative 2u. If you multiply by a negative, it changes direction. Now, there's no reason why this can't be u. Well, then negative 2u would be that. That would be negative 2u. U itself can be what you might consider, oh, it's in the negative direction. Well, I'm not real clear what negative direction is, but I know negative 2u is in the opposite direction. The 0 vector in R2. Everything in this section is about 2 dimensions. It's 2-dimensional. R2. The 0 vector, is defined to be, 3 lines means defined to be this or that. Depends upon what notation you use. Okay. Now, what about the angle between two vectors? So, there's nothing special here. What is u plus the 0 vector. Well, if u is x1, y1, and the 0 vector is 0, 0, well, you add the first components, you get what you get. You add the second components, you get what you get. And x1 plus 0 is x1, y1 plus 0 is y1, and x1 plus y1 is just u. And after all, that is what I called u, but let's state it formally. Let u equal to x1, y1. If you add the 0 vector to u, you get back u. And likewise, if you had u plus the 0 vector, 0 plus u, you have 0, 0 plus x1, y1. You add the first components, comma, you add the second components, and 0 plus x1 is x1, 0 plus y1 is y1. That's u. Okay, so it doesn't matter whether you add, if you do 0 plus u or u plus 0, you get back u. You get back u. And in a later section, we'll be talking about that in more details when we start talking about vector spaces. Now, let me just remind you of the formula for the law of cosines. If this is A and this is B and this is C, we want to talk about that angle, which is I want to see how I want to say this. All right, we'll just call this angle theta. Well, the law of sine say take the sides that make up the angle. And first write down the side opposite it squared. C squared is A squared plus B squared minus 2 times the A and the B times the cosine opposite side C, which is theta. That is the law of sines. Let me rephrase that. That is the law of cosines. Okay. Now, suppose you have vector u going this way and vector v going that way. And now I want to put a vector here going that direction. Well, you start here, you go to v. Plus, you start here and you go to that end, which we don't know. Well, let's see. You started here and you finished here. Oh, that's the same as u. So what do you add to v to get u? Again, if you start at A and then you add on B, this will be A plus B or C. That is, when you add these two vectors, you get this vector. But again, here's the head of the original of vector A, and then the tail for vector B to the head. Well, what do you add to V to get U? Well, you have V and you want to get U. Well, first thing is, I don't want V, so I'll take V away. So far, the sum is 0. V plus negative V is 0. I want U, I'll add U. This vector is U minus V. Vector V plus U minus V gives you vector U. Okay. Let me draw this a little bit bigger. And then we'll apply the law of cosines to this. vector u. This is vector v. And I want to add, so this is v, and I want to add something to it, so this is the sum. I already named the sum. I'm naming the sum u. This must be u minus v. And this is the angle between u and v. Angle theta. I'm going to use the law of sines here. U minus v, the length of this squared, is equal to this squared plus that squared, or the length of u squared plus the length of v squared minus 2 times the length of u times the length of v times the length of v times the cosine of the angle in between. Okay. Now, let me get rid of what's on top. And let's talk about what u minus v is. The first part of the equation says the length of u minus v. Well, suppose I say u is x1, y1, and vector v is x2, y2. Suppose I have that. Well, then u minus v is going to be head minus tail. U minus v. I start here, and I end up there. Well, this point here, that's the same as vector v, which is our x2, y2. We're assuming that that's the origin. Because I can move everything down. If the origin is right here, I can move it so this point is now at the origin. And in fact, that's how I'm defining u and v. Now, this point right here, this is from vector u, which is x1, y1. So u minus v, it's the head minus the tail. It's x1 minus x2, that's the x value, comma, y1 minus y2. Okay. Now, I want to write that point in here because I need the space out here. So now we have what u minus v is. So I could find the length. It's x1 minus x2 squared plus y1 minus y2 squared. I don't take the square root because actually I don't want the length. I want to square the length. Okay. And this is equal to the length of u squared, which is x1 squared plus y1 squared, plus the length of v squared, which is our x2 squared plus y2 squared, minus this, 2 times the length of our of u, x1 squared plus y1 squared, but it doesn't tell me to square the length, so I pick the square root, times the length of v, which is x2 squared plus y2 squared, times the cosine of theta. Okay. get rid of this, please. Okay. It's just a lot of silly algebra going on at this point. I want to FOIL out the left-hand side. This left side. x1 minus x2 squared is x1 squared plus x2 squared minus 2 times x1, x2 plus y1 minus y2 squared. This is y1 squared plus y2 squared minus 2 times y1 minus y2. And it equals to this mess. Well, the first thing I would do is take away x1 squared from both sides, y1 squared from both sides, x2 squared from both sides, y2 squared from both sides. Okay. So what's left over on the left side is negative 2x1, x2 minus 2y1, y2. And this is equal to negative 2. And you know what? Instead of FOILing that, instead of writing the square root of x1 squared, y1 squared, that's just the length of u. Times this, well, that's just the length of v. Times the cosine of theta. Next thing I'll do is I'll multiply both sides by negative. Okay. So we are almost there. We are almost there. In fact, possibly instead of multiplying by negative 1, I take that back. I'm going to divide every term by negative 2. So that becomes plus 2. I divide every term by negative 2. And we're almost done. We're almost done. And now I'm going to write down this on the bottom. On the top, excuse me. x1, x2 plus y1, y2 is equal to the length of u times the length of v times cosine of theta. Okay. Remember that u was x1, y1, and v was x2, y2. Well, look at u dot v. First you multiply the first components, you get x1, x2 plus, now you multiply the second components, y1, y2. But that's exactly what I have here. That is, u dot v, the left side, is equal to the right side. Is equal to the length of u times the length of v times the cosine of theta. Now, one thing I want to talk about is if one of the vectors has no length, that is, if one of the vectors is length 0, you can't really talk about the angle between them, the angle between the two vectors. If one of the vectors is of 0 length, how can you talk about the angle between the two vectors? Okay, when I'm finished erasing this, I'll draw a picture of what I'm saying. That is, I'm saying that it makes no, we can't be talking about the angle if the length of u or v is 0. Okay. If this is u and this is v, we can talk about the angle in between them. But what if u has no length? That is, does u go in this direction, no length? Does u go in that direction, no length? Does it go in that direction of no length? And here's v. Well, if you went in that direction with no length, well then, that's the angle. But if you went in this direction, but no length, well then that's the angle between u and v. And if you went in this direction for 0 length, well then that's the angle. But what does it mean that you went in some direction? What does it mean that you went in some direction? You may say, well, maybe you came from the vector 2, 1. The vector 2, 1 has a length. The vector 2, 1 has a length. And we multiply it by 0, and we get the 0 vector. So now you can say that vector u, let that be vector u. Vector u is in the length, is in the direction of 2, 1, but 0 length. Okay, but there's one problem with that. This is also equal to 0 times the vector 7, 5, which is also 0, 0. So now u is in the direction of 7, 5. What did I come up with, 7, 5? I randomly wrote it down. Okay, so even if you know how a vector became what you did to another vector to get vector u, that is, you multiply 0 by vector v, and you got vector u, you can't talk about a direction for vector u. You can't talk about the direction of a 0 vector. So as I said at the beginning when I drew that diagram, I said, what if u goes in this direction but 0 length? What if u goes in that direction, 0 length? You get different angles. So if we're going to talk about the angle between u and v, it's understood that neither u nor v has 0 length. That is, neither of them are the 0 vector. Okay, and the reason I saw that I needed to state that is because this very, very next line is very important. I want to know what the cosine of the angle is. That is, I don't want to know what the length of u times the length of v times the cosine of the angle is. That is, I'm going to divide, and the right-hand side is just cosine theta. And the left side is u dot v over, I have to divide the left side by the length of u times the length of v. And here is the formula. And it's not because somebody gave it to you. We went through the greatest of details. The only thing I didn't prove was the law of cosines. Watch my trigonometry video. It's there. So the cosine of theta is that formula, which is equivalent to theta is the cosine inverse of u dot v over the length of u times the length of v. Yes, you have to remember inverse trig functions. Okay? Right. So now, we derived the formula rigorously. Now, let's look at an example. Suppose u is the vector 2, 4, and v is the vector 1, 2. We want to find the angle in between. 1, negative 2. We want to find the angle in between vectors u and v. So the angle in between is the cosine inverse of, now first, we'll find u dot v. Okay? U dot v. Multiply the first components. You get 2 minus, no, plus. Then multiply the second components. You get negative 8. That result is negative 6. Okay, the top is negative 6. The bottom, length of u times the length of v. The length of u is 2 squared plus 4 squared, square root. It's 4 plus 16, which is 20. The largest number that I do know the square root of that goes into 20 is 4. It's the square root of 4 times the square root of 5. It's 2 square root of 5. Okay, the length of u is 2 square root of 5. What is the length of v? Well, you square 1 and negative 2. 1 squared plus negative 2 squared. The square root of that is 1 plus 4, square root. It's the square root of 5. Okay. So this equals cosine inverse of negative 3 over 5 because 2 goes into 6 3 times. So the top is negative 3, just like I put. And square root of 5 times square root of 5 is 5. You can calculate it that way, or you can say 3 over 5 is 0.6. The cosine of negative 0.6, according to my trusty calculator, is 53.13 degrees. 53.13 degrees. You want radians? Not a problem. Instead of having your calculator in degree mode, put it in radian mode. So the cosine of the angle between vectors u and v is u dot v divided by the length of u times the length of v. And whatever that right-hand side is, take cosine inverse of it, and you will have the angle. If u is negative 2, 3, and v is 4, 5, v is 4, 5, and you want the angle in between these two vectors. Let's first find the cosine of the angle. The cosine of the angle between these two vectors is u dot v divided by the length of u times the length of vector v. Okay. On the side, I'll compute u times v. Negative 2 times 4 is that number, plus 3 times 5 is that number. So I get 7. Okay. So the top is 7. The length of u. U is negative 2, 3. You square the negative 2. You square the 3. You add them up. Square root sign. Negative 2 squared is 4. 3 squared is 9. You get the square root of 13. Now we find the length of v. The length of v. You square the 4. You square the 5. You take the square root. 4 squared is 16. 5 squared is 25. You add those two numbers, you get 41. The square root of 41. You can't simplify that denominator. Okay, so the cosine of the angle is this. If you want to know what the angle is, you take the cosine inverse of the right-hand side. Basically, I'm switching what's in the boxes. I'm switching what's in the boxes. And if you want me to write theta on the other side, I can do that. I just switch what's in the boxes. So here I have cosine of 7 over the square root of 13 times the square root of 41 equals theta. I just interchanged those two. If there's one price to pay, you have to put -1 up there. That is, theta is, calculate what this is. And then take cosine inverse of that. Theta is the cosine inverse of this. Okay. So let's build up this theorem. In a way, I'll be given the proof before I even state the theorem. And not that I'm a research mathematician, but that is one way of doing research. You start off with some ideas, and then you're like, oh wow, if I put those two ideas together, I have a theorem. Remember that the cosine of theta is u dot v over the length of u times the length of v. Now, suppose u and v are perpendicular. They meet at a right angle. Suppose u and v are perpendicular. That is, the angle between them is 90 degrees. The angle between them is 90 degrees. So then, the cosine of theta is 1. Well, of course that's not true. The cosine of theta is 0. That is, this is 0. But this equals a fraction. A fraction is 0 only if the top is 0 and the bottom is not. Now, before u and v can be perpendicular, u and v can't have length 0. Okay? U and v can't have length 0. Because how can you say what the angle between them are? How can you say what the angle between two vectors are if one of them is 0? So it's understood that when we say, suppose u and v are perpendicular, that means neither the length of u equals 0, nor the length of v equals 0. Well, if the left side is 0, a fraction equals 0 if the top is 0 and the bottom is not. Well, the bottom is not 0. Because if the length of u is not 0 and the length of v is not 0, certainly their product will not be 0. So that means that the numerator is 0. Okay. So we have this. Suppose u and v are perpendicular. That guarantees us that u dot v is 0. If u and v are perpendicular, that implies u dot v equals 0. So what it says is u perpendicular to v implies u dot v is 0. That's what everything above in that box says. It says if u is perpendicular to v, that implies u dot v is 0. If u and v are perpendicular, that's what I wrote, that guarantees us that u dot v is 0. That's what I wrote. Okay, now, let's suppose the other way. Okay. Now suppose u dot v is 0. Suppose the dot product of u and v is 0. Well, the cosine of theta is equal to 0 over not 0. 0 over not 0 is 0. So the cosine of theta is 0. Well, that implies the cosine of theta is 0. The theta is the angle between the two vectors. The cosine of the angle is 0. Well, that implies that theta is 90 degrees, which implies u and v are perpendicular. And now we can state the theorem. We can now state the theorem. Well, let me just write down in short notation what this means. If u dot v is 0, that implies that u is perpendicular to v. Well, if u is perpendicular to v, the dot product is 0. If the dot product is 0, then u and v are perpendicular. So we have this theorem. U dot v is 0 if and only if vector u and v are perpendicular. U dot v is 0 if and only if u and v are perpendicular to one another. So that's important. You take the dot product of two vectors, and none of them are a 0 vector. If you take the dot product of two vectors, and you get 0, and for a second time, none of the vectors are 0. You take the dot product of two vectors and you get 0. The two vectors are perpendicular. I'm going to define this fancy name, orthogonal. U and V are orthogonal if and only if U and V are perpendicular. That is, orthogonal means perpendicular. U and V are said to be orthogonal. So I'm giving a definition. And definitions are always if and only if. So you don't even have to write it. U and V are said to be orthogonal if and only if U is perpendicular to V. They mean the same. U and V are orthogonal. Oh, you mean U and V are perpendicular? Somebody else says U and V are perpendicular. You can say, oh, you mean U and V are orthogonal. Yes, they're the same. Exactly the same. There's no difference between the two. So let's look at an example. U is equal to 2, 5. Now I want U dot V to be 0. Well, 2 times 10 is 20. I want to take away 20. I want to add negative 20. 5 times negative 4. So U dot V is multiply the x values plus multiply the y values, or if you prefer, multiply the first values plus multiply the second values. 20 plus negative 20 is 0. Oh, U dot V is 0. Hence, U is orthogonal to V. U and V are perpendicular. If the dot product of U and V, and note U is not the zero vector and V is not the zero vector. If U dot V is the zero vector, if U dot V equals the real number 0, then U and V are perpendicular. I'll give you a little theorem or a big theorem and only prove some of them. It's a multi-part theorem. Okay. The theorem. If U, V, and W are vectors, and C is a scalar, that is, C is any real number. Let me say any. C is any scalar. Then these four properties are true. A, B, C, and D. U dot U is greater than 0. If you dot a vector with itself, you're gonna get more than 0 if the vector is not the zero vector. U dot U equals 0 if and only if U is the zero vector. U dot V is V dot U. U plus V. You want to dot that with vector W. You can dot U with W. You can dot V with W, and then add them up. C times U dotted with V. You can put the scalar anywhere. That is, this is the same thing as U times CV. U dot CV, which is the same as C times U dot V. And maybe I'll prove B and D. Proof for B. Let U equal x1, y1, and vector V equals to x2, y2. Well, U dot V is x1, x2 plus y1, y2. Multiply the first components plus, and then multiply the second components. Now, the thing is, x1, x2, y1, y2, they're real numbers. I can switch the order that I multiplied. This is x2, x1 plus, switch the order, that's y2, y1. But that's V dot U. V is x2, y2, and U is x1, y1. So V dot U will be x2, x1 plus y2, y1. And of course, you don't need anything that I just circled. I'm just arguing why it's true. There is, having defined U and V in the line above, there is my proof. Now, how about we prove C instead? We prove B, now we're going to prove C. And let me have that extra space. So we're going to prove property C. Theorem C. To save some space, U is x1, y1, V is x2, y2, and W is x3, y3. So proof for C. u plus v is x1 plus x2, comma, y1 plus y2. And I want to dot this with w, which is x3, y3. So let's multiply the first component. You get x1 plus x2 times x3 plus, and multiply the second component. y1 plus y2 times y3. And remember, you want to get u times w, u dot w. That is u w plus the y components of u w. So I distribute. I get x1, x3 plus x2, x3 plus y1, y3 plus y2, y3. But this is this, x1, x3 plus this, y1, y3. I'm going to bracket that, plus what I didn't bracket, x2, x3 plus y2, y3. I'll put brackets around that. Now, this is u dot w. That's u dot w. Plus, the next bracket is v dot w. Make sure you agree with that. Make sure that this really is u dot w. Maybe I'm wrong. But what I showed was, okay, I do have one little mistake at the very beginning. Just got ahead of myself. I only wrote u plus v because I initially only wanted to compute u plus v. But it's really u plus v dot w. This is u plus v, and I am dotting it with w. And I ended up with u dot w plus v dot w. Okay, just a little bit more. It turns out that, well, we're going to talk about a unit vector. A unit vector is a vector whose length is 1. A unit. 1 inch, 1 meter. That's a unit vector. It's a vector whose length is 1. So if you have a vector, and its length is not 1, but you want a unit vector in the same direction as the original vector, how do you compute that? Okay. A unit vector is a vector whose length is 0. Sorry, whose length is 1. Okay, that's a unit vector. It's a vector whose length is 1. Nothing major going on there. Now, let x be any non-zero vector. Let x be any vector except the 0 vector. Be any non-zero vector. Then, if I calculate u by multiplying vector x by 1 over the length of x, this vector, which generally I like to write like this, is a unit vector in the direction of u, in the same direction of u. Why? Because the length of x is positive, and 1 over a positive number is positive. And I'm scaling, so this is my c. Remember, c times vector x. If this is positive, then c times x is in the same direction of x. Oops. It's in the same, u is in the same direction of x. Okay. Now, I'm going to move on to the theoretical exercises. But in this section, it's just going to be exercise, just one. It's just going to be one. We want to show that if W is perpendicular to U and V, let me just state this first. Show that if W is perpendicular to vector U and V, then W is perpendicular to what's called a linear combination. It's perpendicular to a multiple of U plus a multiple of V, where R and S are any scalars. Well, so if they're perpendicular, if this vector and this vector are perpendicular, then their dot product should be 0. Then their dot product should be 0. Well, the last theorem said we can dot those two plus and then dot those two vectors. But another theorem says that we can bring the scalar in front. The scalars R and S in front. This is R times W dot U plus S times W dot V. But W is perpendicular to U and V. So W dot U is 0 plus S times W and V are given to be perpendicular. So that's 0, the 0 vector. So the 0 vector plus the 0 vector, which is the 0 vector. That completes the theoretical exercises and this video, this section.